Newton's first law. So Newton's first law says a body's velocity remains constant unless the body is acted upon by an external force. So that is, a body is either at rest and it doesn't move because the overall force is zero, or else the body is at a constant speed and it stays at a constant speed unless it is acted on by some overall force. So if the body is moving along at 5 meters per second and the forward force is equal to 10 newtons, the backwards force is always also equal to 10 newtons, then it is not going to move because there's no overall resultant force. This example says the body below is stationary. Find the values of the unknown forces. So if it's stationary, what you can do is you can just say, you know then that the forces, the overall resultant force in any direction is zero. So if you resolve vertically, I'm saying the force up, which is R, is equal to the force down, so R is equal to just 30 newtons. Likewise, if we resolve horizontally, the force right is equal to the force left, so F is equal to 30 newtons. Next example, it says the body below is moving with a constant velocity. Find the values of the unknown forces. This example throws people because you've got this velocity. There is no need to, because of Newton's first law. It doesn't matter if it's either stationary or it's moving at a constant velocity. The same thing happens. The overall resultant force in any direction is zero. So if we resolve vertically, you've got your force up is equal to your force down. So R is equal to 100 newtons. If you resolve horizontally, your force right, which is F plus 10 in this case, because you've got the F and the 10 going to the right, is going to be equal to your force left, which in this case is just 75. So a tiny wee bit of mathematics to do here. F is equal to 75 minus 10. F is equal to 65 newtons. Okay, Newton's second law, this is where it gets a wee bit more interesting. Newton's second law is that if there is an overall or resultant force acting on a body in any direction, then the body will accelerate in that direction, i.e. its velocity will change. The larger the resultant force, the greater the resulting acceleration. The acceleration of the body is directly proportional to the resultant force acting on the body. So this gives rise to the famous equation F equals m times a, and can you add in, that's just F is equal to ma, that's how we will be referring to it. Where the force is in newtons and the mass is in kilograms, gives a resulting acceleration which is in meters per second squared. Also, can you just say, these units quite often are referred to as ms to the minus 2, and you quite often see that in physics, so ms to the minus 2. So meters per second squared is the same as ms to the power of minus 2. Okay, Newton's third law says, for every action there is an equal and opposite reaction. This means that if a body experiences force in a given direction but does not accelerate, then an equal force acting in the opposite direction to cancel out that force must exist. This is most commonly seen by objects in contact with a surface. There is always a perpendicular reaction between an object and a surface it is in contact with. And we will see this, we will call this force the normal reaction. So find the acceleration of an object below and the value of r when x has a value of. So we have a few different versions of this to do. So we'll do part A and see what we're going to do. Okay, before we do part A, actually, we will just resolve vertically. Vertically in this question, it's going to be the same. So we're going to resolve vertically, and your force up is equal to your force down. So it's 100 newtons. And that is going to be the same. And just say that will be the same for each part. I get it right. That will be the same for each part. So it doesn't matter if you increase your x, so if this thing increases, your normal, this vertical plane, nothing has happened to it, so it is going to stay the same. Okay, so for part A, B, and C, all we have to do is work out, use F equals ma to find the acceleration. So we're going to resolve horizontally, but we're also going to say use F equals ma. Now people set this out very, very badly. Notice it's F, so force, so only the force goes on the side, is equal to your mass, which is 10 in this question, times your A, which is what we're trying to find. So going to the right, the force we have going to the right is 30. The force we have going against that is x, so it's 30 minus x is equal to your mass, which is 10, times your acceleration A. Now in this case, The x is equal to 0, so it's just 30 is equal to 10a, which means a is equal to just 3 meters per second squared. For part B, we're going to do the same. We're going to resolve horizontally. We're going to use F equals ma again, and we've got 30 minus my x, which this time is 15, is equal to 10a. So 15 is equal to 10a, which means your a works out to be 1.5 meters per second squared. And your last part for this one, part C, we're going to resolve horizontally again, and we're going to use F equals ma. So your force pulling is 30, going against that is your x, and in this case x is 30, and that's equal to your mass, which is 10 times your acceleration. So 0 is equal to 10a. A just works out to be 0 meters per second squared. And there we have our 3 answers. Okay, next example says a car of mass 830 kilograms is being driven by a tractive force of 3,200. There is a constant resistance to motion of 0.5 newtons per kilogram. Find the acceleration of the car to 2 decimal places. Okay, a little diagram here would be very helpful. I'm going to say it's moving this way. So how you denote acceleration is a double-headed arrow. So I've got my A going this way. The attractive force is a force that is pulling it, and my constant resistance in this case is 0.5 newtons per kilogram. So just do 0.5 times your mass, which was 830 kilograms, and so 0.5 times that is going to be 415 newtons. So that's your diagram. You would have a normal reaction here. You would also have the weight, which I don't think we've talked about just yet, but you would have the weight, which would be mg, but we don't even have to mark them on for this question. There's absolutely no need. So that's all the information we need. That is fine. I'm going to resolve horizontally, and I'm going to use F equals ma. So my pulling force is 3,200. Going against that is 415. My mass is 830, and that's my A. Tidy that up. That's a wee bit of a mess. Tidy up. That's 2,785 is equal to 830A. And then just divide across by the 830, and you will get your A is equal to 3.36 meters per second squared, and that was to 2 decimal places. Okay, next example says a super fun child's toy of mass 2,000 grams is able to accelerate at 0.1 meters per second squared with negligible resistance to motion. Find the forward force produced by the toy. Okay, we're going to jump into part 1 first, and then we'll come back and look at the rest of the question. So let's get our diagram drawn first, and then I can scroll down. So the diagram for this would be quite simply, I guess, find a forward force produced by the toy. Your forward force is the only thing you've got. You've got no resistance. So 0.1 meters per second squared was your acceleration, and you knew the toy was 2,000 grams. Convert that to kilograms, of course, so 2 kilograms. So for this one, we will have a look, and we will say, we'll use F is equal to ma. So F is equal to 2 times 0.1. You're not going to get many questions easier than this one, so 0.2 newtons. Okay, it says the toy has a turbo mode which allows it to accelerate from rest at a whopping 2.5 meters per second squared for 4 seconds before the battery is depleted. If there's resistance to motion during the turbo mode is 5 newtons, find the forward force produced by the toy. So a diagram again, and then I can scroll down. So I will scroll down a wee bit in a way, so I can get this drawn. Okay, the mass hasn't changed. Your resistance to motion is 5 newtons. We have F. I do not get confused with this F from earlier on. It will have changed, but As we know, it is now, there's acceleration taking place of 2.5 meters per second squared in this example, and then we're good to go. So that's our diagram. Again, we're just going to use F equals ma. It is F equals ma, but I'm going to say use force equals ma. So I'm saying force because there's an F here, and it's the overall force. So the overall force in this case is the F minus 5 is equal to 2 times the A, which is 2.5. So that's going to be F is equal to 2 times 2.5 is 5. Bring the other 5 across. That's what you have. So your F works out to be 10 newtons. So that's what we've got so far. Okay, let's have a look. Part 3 of this question. It says, state any assumptions. Part 3, here we are. Part 3 says, find the distance the toy can travel during 4 seconds. During the 4 seconds it is using turbo mode. So this is going back to a Suvat equation. So it starts from rest. It accelerates at 2.5 meters per second squared. It does this for 4 seconds, and S is what we want to find. So we want to find the S. So we're going to use S is equal to UT plus a half AT squared. S is equal to 0 plus a half times 2.5 times 4 squared, which means your S works out to be 20 meters. Okay, last question. It says, state any assumptions you have made throughout this question. These are my least favorite type of questions. Anything at all, it's just like a real life assumption. So I'm going to say the assumption it's on a flat surface, where there's no other objects on the surface or anything out for it to bump into. I'm just going to go with assuming the toy is on a flat surface. And that's it. Okay, so that's that example done. Assuming the toy is on a flat surface was the assumption we did, but you could have had loads of other ones. Anything sort of plausible, really, if you put down in an exam, they're going to give you the mark for it. Okay, this example says, find the force required to accelerate a 1.5 kilogram object from 2.2 meters per second to 7.9 meters per second in 2.28 seconds. Hence or otherwise find the distance traveled by the object during the acceleration. Okay, right. First of all, we need to find the acceleration. So we're going to say our U is equal to 2.2. Your V is equal to 7.9. It does that. It accelerates from between those two speeds in 2.28 seconds. So what we want to find is the acceleration. So use your easiest of the Suvat equations. V is equal to U plus AT. Fill in what you know. 7.9 is equal to 2.2 plus 2.28 times your A. And a wee bit of working out, you're going to have 5.7 is equal to 2.28 times your A. Then your A works out to be 2.5 meters per second squared. So bang on 2.5. And if I got 2.5 as my answer, I'd be fairly happy with that in an exam. Once you've got your 2.25, what you can do is draw a wee diagram. Try and do a better one than I've just done. And we'll mark on the mass was 1.5 kilograms. We wanted to find the forward force that would produce that acceleration. Mark on your acceleration, so double-headed arrow, remember, 2.5 meters per second squared. And then we're going to use, there's no other forces, so we're just going to say use F is equal to ma. So your force is equal to your mass, which is 1.5, times your acceleration, which is 2.5. So your F, your force, works out to be 3.75 newtons. Okay. Next part of the question says, hence or otherwise, find the distance traveled by the object during the acceleration. So again, it's just a Suvat question. U is equal to 2.2, your V is equal to 7.9, your T was 2.28, S is what we're looking for, and I'm going to use S is equal to a half U plus V times T. Remember, all these formulas are given to you at GCSE Further Maths, so you can check those on your formula page in an examination. If you have any doubts at all on what you're putting down, just check it, just be sure to be right. And if you punch that all into your calculator, it will not show any more working out, absolutely no need. And if you punch that into your calculator, I've got 11 points. I'm going to have to pause the video here because I can't read my. Okay, so we got, when we did that, we got 11.51 meters, and that is the answer. That's it. I would just leave it as that. Okay, next bit says, when a body experiences a decelerating force, the laws still hold. This is often seen whenever a resultant force acts opposite to the current direction of motion. We must watch our choice of positive direction in these questions and be aware of the relevance of negative answers. This example says, find the braking force required find the braking force required to bring a car of mass 0.8 tons to rest from a velocity of 30 meters per second in 5 seconds. Okay, first of all, we'll need to address what a ton is. So let's say 0.8 tons is equal to 0.8 times 1,000 kilograms, which is going to be 800 kilograms. Okay, we want to find the braking force required to bring a car of mass 0.8 tons to rest from a velocity of 30. So your initial velocity is 30. Going to rest means going back to 0, and he's doing that in 5 seconds. So we need to find our acceleration first. So we're going to use V is equal to U plus AT. So 0 is equal to 30 plus 5A. So minus 30 is equal to 5A, which means your A works out to be minus 6 meters per second squared. Oops. And we do a diagram, try and do a horizontal line, and you've got your 800 kilograms as your mass of your car. And I am going to say it is going this way. Now what I like to do is I want to put the direction the thing's going, even if the acceleration is negative. So it's going at an acceleration of minus 6 meters per second squared. And what's causing it to slow down, I'm going to call this R here for my resistive force. So I'm going to say resolve horizontally, and I'm going to use F equals MA. Now, wee arrows is important to use. My arrow is going to the right, my R is going against that, so it's minus R is equal to my mass, which is 800, times my acceleration, which is minus 6. So minus R works out to be minus 480, minus 4,080, I apologize, and then that means R itself is 4,080 newtons. So just to tidy up, just to be absolutely sure, the examiner knows what you're talking about, and just say the braking force is equal to 4,800 newtons. So a wee word every now and again makes it all very clear. Okay, our last example says a lorry of mass 1,500 kilograms is accelerating at 1.3 meters per second squared against a resistive force of 500 newtons. Find the attractive force produced by the engine. So again, diagram for this first part. You've got your wee box for your vehicle, whatever it is. So a lorry in this case, 1,500 kilograms, and it's accelerating, double-headed arrow, at 1.3 meters per second squared, against a resistive force of 500 newtons, and I've got my attractive force. I'm going to call it P. I quite often use P for my attractive force. Avoids me using F, so I'm going to use F is equal to MA. So my forward force is P. Going against that is my 500, and that's equal to my mass, which is 1,500, times my acceleration, which is 1.3. So that means P minus 500 is equal to 1,500 times the 1.3 is 1950. So P is equal to 1950 plus 500, which means your P works out to be 2,540 newtons. Part 2 says if the engine suddenly switches off, find the deceleration assuming the resistance is unchanged. Right. If something changes, please do a new diagram, because too often people don't do a new diagram, and then what they've got in their head is the first diagram, and that's why they mess it up a wee bit. So your mass is still the same. This has gone, so don't be putting a P in, it's gone. It's going this direction still, but the acceleration's changed, that's A. The resistive force is unchanged, so it is still 500. So again, we're going to resolve horizontally, and we're going to use F equals ma. So going to the right, we don't have anything going to the right. What we're going against it is the 500, so it's minus 500 is my mass, which is 1,500 times my acceleration. And a wee bit of working out then, that means your A works out to be minus 1/3 meters per second squared. Okay, it says if the engine suddenly switches off, find the deceleration. So didn't find the we've just found the acceleration. So just say, therefore, your deceleration is equal to 1/3 meters per second squared. Okay, last part of this question. It says a lorry was travelling at 60 kilometers per hour when the engine was switched off. Find the distance travelled to the nearest meter before the lorry comes to rest if an additional braking force of 2,250 is applied. Okay. I'll do a diagram first of all, and that was 1,500 kilograms. It was an additional 2,250 onto our we already had 500, so that's going to be 2,750. Oops, not newtons. Sorry, it was newtons. 2,750 newtons, and we're going to have a new acceleration. So we're going to resolve horizontally using F equals ma. So that's minus 2,750 is equal to 1,500a. Which means your A works out to be minus 1.56. Leave it as that. That's perfect for your acceleration. Okay, we have got to find the time it takes for it to find the distance travelled before the lorry comes to rest. So we've got to find the initial velocity. The initial velocity is 60 kilometers per hour. Now, let's get that into minutes first of all. Get that into minutes. Get that into meters first of all by multiplying it by 1,000. We get it into meters, because that's going to be that amount of meters per hour, and then get it down to minutes by dividing by 60, and get it down to seconds by dividing by 60 again. So go through that again. You have 60 kilometers per hour, which would be 60 times 1,000 meters per hour, and then you're going to have 60 times less in 1 minute. So divide by 60 to get down to 1 minute. Divide by 60 again to get down to seconds. So if you do all of that, what you're going to get is your initial velocity is 16 2/3, and that's going to be meters per second. So now we've got our acceleration in meters per second squared and our velocity in meters per second, so we're good to go. So you've got your U is equal to 16 2/3. Your acceleration is minus 1.56. Your final velocity is 0, and we want to find the distance that it takes us to do this. So we're going to be using v squared equals u squared plus 2as, and that's just going to be 0 is equal to whatever that is, 16 2/3 squared plus 2 times the minus 1.56 times your s, and a wee bit of working out which I'm going to omit because I have run out of space. So all you do is bring that across the other side, the 2 times the minus 1.56 s across the other side, and then divide across by it. So what you're going to get is your S is equal to 75 and 25 over 33. Thankfully it said to the nearest metre, so it is equal to 76 metres, and that is to the nearest metre. Done. Okay, that is us done. So we've covered quite a bit of stuff there in our using our Newton's laws. That's the end of the video.